All right, let's dive into one of the most exciting parts of science, the journey from a simple question, that little nagging, what if, all the way to a real discovery. How do we actually turn pure curiosity into an answer?
I mean, have you ever really thought about that? Do these brilliant ideas just pop into their heads out of nowhere? Is it some flash of genius that the rest of us just don't get? Or is there something more going on behind the scenes?
Yeah, spoiler alert, it is not magic. It's not a random bolt of lightning. It's a process, a structured, repeatable process. And it all kicks off with one of the most powerful tools in the entire scientific toolkit, the hypothesis.
So let's get right into it. What exactly is a hypothesis? And why is it the absolute starting point for pretty much every discovery we've ever made?
At its core, it's actually pretty simple. A hypothesis is just a proposed explanation for something. It's an educated guess about the relationship between two or more things, or as scientists like to call them, variables.
Now, hypotheses really come in two main flavors. On one hand, you've got the experimental hypothesis. This one's all about cause and effect. It predicts that if you do X, then Y will happen. So in our example, using CBT causes less relapse. On the other hand, there's the non-experimental hypothesis. This just predicts a relationship or a correlation. It suggests two things are connected, but it doesn't say one causes the other. It's just noticing a pattern.
Okay, so you've got an idea. That's great. But is it a good hypothesis? Well, it turns out there are 3 essential rules. Think of them as quality control checks that help build a really solid foundation for your research. And here they are, the 3 pillars of a great hypothesis. It's got to be a synthetic statement, it has to be testable, and it needs to be parsimonious. Now, I know those might sound a little academic, so let's break down what each of them really means.
First up, it must be a synthetic statement. All that really means is that the statement could be true or it could be false. We just don't know yet. Think of it this way. A real hypothesis has to put some skin in the game. It has to be falsifiable, meaning there has to be a possibility that the evidence could prove it wrong. If it can't be proven wrong, it's not a hypothesis. It's just a fact.
Second, and this one is absolutely crucial, it has to be testable. Can you actually design an experiment to check if it's true? Can you change one thing, the independent variable, and then measure the effect it has on another thing, the dependent variable? Because if you can't test it, it's a fascinating idea for sure, but it's not a scientific inquiry. It's stuck in idea land.
And third, it needs to be parsimonious, which, I know, is a bit of a mouthful, but the idea behind it is simple. Keep it simple. The best explanation is often the most straightforward one. A good hypothesis doesn't have a bunch of extra, unnecessary parts. It's like having a clean, simple blueprint for a house versus one that's overly complicated. The simple one gives you clarity and a clear path forward.
All right, we've got the rules down, but how do scientists actually come up with these ideas in the first place? Well, they generally follow 2 main paths of reasoning to build these blueprints for big ideas.
So on one side, you have induction. This is bottom-up logic. Think of it like a detective at a crime scene. You gather specific clues, specific observations, and you piece them together to build a broader theory about what happened. Then on the other side, you have deduction, which is top-down. This is where you start with a big, general theory, kind of like a rule book, and use it to make a very specific prediction about what should happen in a new situation.
But here's the really cool part. Scientists don't just pick one and stick with it. They use both, together in this powerful, never-ending loop. You observe stuff, you use induction to form a general theory, then you use deduction to make a new, specific hypothesis from that theory, and then you test it. And guess what? The results from that test, they become your new observations, and the whole amazing cycle starts all over again.
So we have the rules, we have the methods, but where does that initial spark of an idea come from in the first place? Where does inspiration strike?
Well, it usually boils down to one of 3 places. The most common source, by far, is just digging into research that's already been published. Then you've got serendipity, the happy accident. And finally, there's good old intuition.
And let's be real, that first one, reviewing past research, that's your absolute best bet. Why? Well, it tells you what questions are still out there, waiting to be answered. It can spark totally new ideas. It can point out other factors you might not have considered. And maybe best of all, it shows you what problems other people ran into so you can avoid them.
Now, what about those happy accidents? Those moments of pure luck, like discovering penicillin? Well, there's a famous saying that serendipity favors the prepared mind.
An accident is only a discovery if you have the knowledge and the expertise to look at something unexpected and go, wait a minute, that's important.
And that brings us to intuition, that gut feeling, right? That sense that you're onto something. But here's the thing about intuition in science. It isn't just a wild guess. It's an educated guess. It's a feeling that's been shaped and guided by all that research you've been reading. Your gut knows what to look for because your brain is already full of information.
Okay, so we've crafted a strong, testable, simple hypothesis. Now what? Let's zoom out and see how this one little idea fits into the bigger picture of how science actually gets communicated and how our collective knowledge grows.
So when a scientist is writing up their research, the introduction section isn't just a warm-up. It's where they build the entire case for their hypothesis. They carefully walk the reader through what we already know from past research, point out a gap or a question, and then present their hypothesis as the perfect logical next step to help fill that gap.
You know, over time, as lots of different experiments test similar hypotheses, we need a way to see the forest for the trees. That's where this incredibly powerful tool called a meta-analysis comes in. You can think of it as a study of studies. It pulls together the results from tons of experiments on the same topic to see what the overall trend is. It gives us a much more confident, big-picture view of a finding.
So you might be thinking, this is all great, but how do I start thinking this way? Well, it's actually easier than you think. Here are 3 things you could do right now. Go find a science journal and just read an article. Or next time you're at a coffee shop or a park, just watch people. Observe what they do. Or pick a real-world problem you care about and just start brainstorming. What do you think is really causing it?
Because that's really what this all comes down to. A hypothesis isn't some scary, complicated thing. It's just a clear, testable question that's born from simple curiosity. And now you have the blueprint. You have the tools. So what are you curious about? What question will you ask first?